So today lecture we actually first we will talk about different kinds of compression that we can apply on neural networks for being feasible to deploy our networks on embedded systems. Okay, so first let's start from why we need to compress our neural networks. Yeah. Okay. So deep learning is everywhere. So we for deploying algorithms when we have a limit of power, or actually we have battery constraint, like in phones, drones, robots, glasses, autonomous vehicles. We should be aware about how many power our networks consume. And this is a kind of big, huge problems because as we know, deep neural networks have a lot of parameters. Yeah, and they consume a lot of they consume a lot of power. Need a huge GPUs or CPUs for doing the computation. So today we will see a lot of ways how to reduce the number, also the number of parameters and their power consumptions by reduce the precision of the parameters. Okay, so actually we will talk about pruning and quantization. So why smaller models? This is actually a famous table of from Bill Dell that showing that doing operation on floating point or 32 bits and doing operations, it's actually we need a lot of energy, and we prefer to reduce. Okay, so here we actually we not really see it, but when we working with operations that are less than 32 bits, like 8 bits, it consume less energy. So we prefer to work with smaller precision operators. Okay, so great. So first method for reducing the computational is actually by pruning, and the first method of pruning that I will show you is singular value decomposition. So one of the it's actually work from this work was done 5 years ago. So 5 years ago, most of the network was composed at least with 3 or 4 fully connected layers. Okay, this tandem it's not so quite. It's actually for now. Most of the deep neural networks consist with one fully connected layers or without fully connected layers. But against fully connected layers have a lot of need a lot of weights because we are doing operation of each tensor to each tensor. Yeah, so we can divide our weight matrices to singular decompositions. Okay, by using matrices from U and V transpose, and S is actually our diagonal decreased magnitude matrices that we multiply our both U and V. Okay, so by reducing the rank of this matrix of S, we can reduce the number of computational that we need. Okay, again, we increase. We can approximate by we can take only n first or t first components, and then actually we can dismiss or remove the last components, and we will reduce the whole matrix. Sorry. Okay. Great. So by only keeping t singular values with largest magnitude, we can approximate our W with getting more lighter metrics. Okay, so here we assume that actually we're taking rank of WT, and this way we will do less computations. Okay, so let's talk about the storage and the that we need. So for original W, we need O m by k complexity, and for our pruned or reduced W, we need only mt plus t plus tk complexity. And of course, it's actually here we need less storage. It consumes less energy and give us options to be able to work with less power demand hardware for deploying our algorithm. So the compression rate of our network is actually mk divided by t mk plus 1, and we have some theoretical error that actually we are bounded by the normal of A multiplied by st plus 1. Great. So this method was evaluated on ImageNet. Actually, it's AlexNet. It's 5 convolutional layers and 3 fully connected. So as we can see here, we take with using different k parameters. It's actually our rank of metrics. We can reduce the factor of weights by 13, and only by increasing the error by 0.8. Okay, so again, with low degradation in accuracy, we achieve huge saving of the weight reduction. Okay.
So why we are not build a smaller FC layer?
Again, why we don't?
We don't build the FC layer inherently smaller than.
Yeah. So again, so if you can build a smaller FCL layer, but if you're assume that you cannot change your network. Okay, so if you cannot, so if you have existing network and it contains like VGG network, that contains a lot of parameters in fully connected layers. Okay, so you need to find a way how to reduce the number of parameters. But again, yeah, as I said before, the novel architecture actually have very small fully connectional layer. Okay, because this is one of the way how to reduce the number of computationals that you need. You make slight fully connection layers with only few tensors. Okay, great. Yeah, any questions? Again. Why you're asking about the hyperparameter? Look, they did a lot of experiments, but they showed only the best. They showed only the best ones. Yeah, so it works it works better for these parameters again. Yeah, so this is cherry picking. Okay, this is only cherry picking. Okay, great. So let's going. Okay, so the benefits is, of using singular value decomposition is reducing the memory footprint. It can be reduced in dense layers by 5 and up 13 factor, and we make speed up by reducing of computational complexity by speed up factor of this one, mk divided on t multiplied by m plus t plus k. And one of the phenomenon of use of actually doing pruning by SVDs, like pruning, yeah, because we prune some weights, is that we have regularization. So it's very interesting, and the phenomenon, it's actually very highly used. And when I will show you the next slides, you will understand why now one of this actually why people use more common pruning ways. So low rank projections is effectively decrease the number of learned parameters, and this way, when we learn less, we generalize better. Okay, it's actually one of the now most common results in deep learning. And paper applies again SVD. We apply it after we train our model. So first we train our model as usual, and then when we have pre-trained weights, then we apply it to our SVD. We are not doing it, but don't do it the training by scratch using SVD. Okay, we first getting results, and then we applying SVD. Yeah. Questions until now? Now we are going for other models. Yeah.
So basically, like the idea is that after you do the training, you believe that some of the weights you don't really need it.
Yeah. The main idea is that you have a lot of redundancy in the learning. A lot of parameters are actually are not used during the training. Okay, so you don't need them they are not the part of the if this function, if the our learning algorithm is function of some parameters, so they are not in the function.
Yeah. Why not like train the net and then do the SVD?
Yeah.
You say you need only like 800 parameters.
Okay.
So change the hyperparameters of the net and retrain it.
No, SVD is we do retrain. SVD, all the algorithms they work like we pre-train it on we pre-train it, and then we applying iteratively SVD. Yeah, but we do retraining. We first train it or in original stuff or with all parameters. Then we applying SVD, and then we fine tuning. We actually because we want to achieve. We want to we want to optimize it. We want to get the best loss error. So we doing it iteratively. Of course, we are doing fine tuning. It's not post training method. You are not you should of course. So I will inside this fact. So emphasize this fact. So we do again retrain. We're retraining by using SVD. How many iterations you need? It depends on the compression rate that you want to achieve. If you want slight compression rate, you need less epochs. If you want more compression rate, you apply more epochs. Yeah. So it's not post training. It's not only applying SVD on pre-trained network and that it's actually in the most cases you need more epochs for retraining rather than for getting original results. Yeah, but we call it fine tuning. So it's all all the all the method is like we are doing fine tuning. We are not mentioning how many the papers not mentioning how many epochs they need for getting the results. Yeah. Questions? Great. So okay, now we'll talk about convolutions. Of course, so convolutions in the modern neural network is actually the most of the weights and the calculations are actually you need for doing matrix for doing convolutions. So most of the time the convolutions layers are spent is actually here. So this is our kernel of convolutions. Yeah, so we applying our kernel and finding the output features. So it's functions of x and y, and then you get your identity multiplied by weights. Okay, so how to do more efficient convolutions? So as you know, is that the original or the common way to do convolutions is 3D convolutions, that we are taking our cube. This is our convolutional cube. Convolutional cube is his dimensions is channels by the way by the picture image size y by x. Okay, and then we are actually applying all our feature map by multiply our weights on feature maps. Okay, so one of the way to reduce the number of calculations that during the convolutions is to divide it to 1D convolutions over different axes or directions. So what we will do, so first we will take our convolutions in the channel size by channel by 1, okay, so it's only it's 1 by 1 matrix over along channel feature maps, and then we are getting some 1D matrix, and then we are applying the convolutions on the y direction, and then applying convolutions on the x direction. So this way we are getting our 3D feature map only by dividing and doing our convolutions separately. Okay. So this is one of the way. So flattened. This method called flattened convolutions. So during our feed forward, so there are no any change in our back propagation. Okay. So we have we have no different in our in the storing, in how we store our weights or how we do our optimizations. Only how we applying our feed forward. Okay. So during feed forward we are doing less computations. Okay. And then we of course optimize the loss function. Okay, and then we are doing iterating only. We are only replacing the feed forward iteration by from cube to flatten to flatten convolutions. Okay, so as you can see, this is our f. We are instead making one big summing on all cube. We are making our summing on each of the 1D convolutionals separately, and the compression and the speed up of this method, the parameter reductions, is we are taking from x multiply y multiply c. It's x plus y plus c. Okay. So we reduce our computational complexity that we need for computation, for doing computation. Okay. The second one is operation reduction. So before we had m by n by c by x by y. Now we have actually only m by n and c plus, and here we instead of multiply, we are only summing. Okay, so we reduce both on parameter reduction and on the operation reduction using flattened convolutions. Okay. Okay. So flattening speedups. So this actually we have here some results. So we have the experiment was done on 3 convolutional layers, filters 5 by 5, with 96 and 125, 28 and 255, 56 channels. Okay, so you have 3 convolutional layers with a different number of channels. Okay, and here we actually can see then using our input that on given input image size, the backpropagation runtime and the feed forward runtime is actually dramatically decreased. Okay, you can see here. So this is the red plot is our flattened convolutions, and the blue plot is our blue line is our baseline. Okay, so we reduce dramatically our time that we need for calculate the operations. Yes. What? Why does it compare with? Okay, this work was done in from 2014. You know, from this step, the GPUs only start to rise. So it was before GPU era, okay, or in the start of GPU era. Of course, the research that was done in past 3 years, all of them do. Again, you can see it's a very shallow network. Okay, it's only 3 convolutional layers, so they can afford themselves to do it on CPU. Okay. But of course, when if you reduce the numbers of the CPU, you will of course reduce the numbers of the CPU. Only the offset is the difference, yeah, because it doesn't really matter because you reduce the number of operations. Yeah.
Why do we have higher accuracy for the flattened one? And then
Okay, yeah, you're asking here why we have reason. Yeah. So again, it's the regularization. Okay, using what? Okay, so doing pruning, it's acting like generalized better. Okay, so all these ways so you can observe when you reduce the number of parameters, you actually in some cases even getting better results rather than the full network.
have to minimize that, like the minimum required network for this specific case, it won't give us the better results in terms of accuracy. Like if there is nothing to reduce, we won't get the better generalization.
If there's nothing to reduce,
Basically, this case is like the network is basically we can say that it's too big for the case it has. Like
some of the yeah. If you cannot, you're right. So you are saying that if we cannot reduce, if we have not over parameterization, so we cannot. Yeah, of course. So it's if you cannot reduce it, it means that all of the parameters that you have are including in the function that we compute. Yeah, of course. But in the most common mostly it's not the issue. Mostly you have over parameterization. You have more parameters than you need. Okay. Okay. So now I will present you another way to reduce the number of the computations that you need for calculating your neural network. So first time I will start from work that done by Alex Krzyzewski and George Hinton. It's not famous work. You're not familiar with this work. It's AlexNet. Okay. So I just kidding. So AlexNet is the first it actually was first a success of neural networks. Yeah, it was first work that they outperformed by far all previous computer vision approaches. for classification. Okay, so until 2012, people did classification not with deep learning. Yeah, they did classification with like filtering, using edge detection, canny, and other stuff. Yeah, but not with using deep learning. But then came Alex Krzyzewski. He was George Jeffrey Hinton master student, and he actually proposed a network for classify ImageNet and one of the large scale data sets. And he also proposed the way how to do it. So this way, in 2000, his network was consist of from 50 million parameters. So he wants to train it with GPUs, and he actually the GPUs in 2012 their size was maximum, I think, 1 or 2 gigabyte of RAM. So he cannot fit his network to GPU. So what he did, he divided the network for 2 GPUs. Okay, so he called it group that he did grouping. So he took all the channels and feature maps, and he divided for 2 groups. One groups worked on one GPU, and the others on another GPU. So he divided the training for 2 GPUs and did it distributing by actually simultaneously. So both of the filters multiplications happened actually in one time step. So and then he actually and the other and the it was the and then he beat all the works that done before, and now it's one of the cited work ever in deep learning. Only I think backpropagation by Hinton have more citations, but it's actually the must work that everyone is cited when he's doing deep learning. So okay, so what we can do, we can divide our all convolutional filter to two filters. Each of them actually will have channels. We divided by channels by half of the number of channels, and we will do this multiplication simultaneously. Okay, and as you can see here. When we use no groups, we achieve some results. And if we use 2 groups, we actually reduce the number of calculation at each step by half. Okay, we not really decrease the number of weights that we have. Why? Why we do not really decrease the number of weights that we have? Yeah, because we only divide it. But in the same step, we do half of computations that we need. Yeah, so we do half of the computations that we need by using 2 groups this way, and we can fit larger networks because we can do distribute learning. Yeah, and we actually here he showed that the results we actually achieve better result than using no groups. Again, is the same phenomena of regularization. Okay, so and 4 groups actually they achieve same a little bit more, but it's actually negligible accuracy error rather than no groups. And of course, the calculation per step is going by factor of number of groups that we use. Okay, so this work actually propose how you can do distributed learning and by using more GPUs for getting faster results. Questions? Good. Okay, so now I will show you. Now we will talk about how we prune our network and how it helps to reduce the number of parameters. So, Hansong, okay, he is now professor at MIT, in 2015 introduced in NIPS. As you know, it's the best one of the best deep learning, machine learning conferences. His work, so the work is learning both weights and connections for efficient neural network. So again, most of the regular work are actually are only training the weights for getting that accuracy. So he add one constraint, one more constraint to his loss for getting not only optimize the weights for getting for the performance, but and the second constraint in how to prune. Okay, or actually how many tensors you can remove by and getting the best accuracy. Okay, so we have two constraints: one on complexity by pruning, and the second on the your optimization your problem. Okay. Questions, guys? This is dropout is kind of pruning. Yeah, of course. So dropout is one of the pruning. Okay, it's one is type of pruning. Okay, great. So what we do? So this is actually what we have before pruning. We have if we assume fully connected layers. So we have all these kind of connections. Then when we prune, we have less connections. So how the algorithm works? So we choose a neural network architecture. We train the network until we have reasonable solutions obtained, and then we prune the weights of which magnitude are less than the threshold. So we set some hyperparameter as threshold. Okay, we prune the weights that are actually below. We remove the parameters that are below the threshold, and then we train the network until a reasonable solution again. So this is our second iteration. It's like fine tuning. Okay, and then we iterate to step 3. And actually, this set of the 3 and 4 we are doing iteratively until we have desired results. Okay, until we cannot prune more. Okay, we are prune achieving the base result that we can achieve, and then we prune more. We are pruning more and more and more until we have degradation in the results that we want to stop our training. Okay. Okay. So you are asking if this method can apply to convolutional neural networks. The answer is not this way. So convolutional neural networks and dropout again, as you mentioned before, it's actually the methods for fully connected layer. You have to make extension to more than more than two-dimensional structures, and then you can do it. But again, if you have I'm not showing in this. It's actually most advanced works, but you are pruning when you are pruning for convolutionals. You are pruning filters. You are taking filters and then you remove it. You are removing the whole filters. No. You cannot. It's actually you want to do it, but it's very sophisticated. It's actually you can. It's very problematic to do it because you cannot do efficient computational if you are taking only the part of the, if you remove only the part of the weights in the filter. You prefer to remove filters, for all filters, okay? Yeah.
What do they mean here by magnitude? It's the it's 3D.
Your values, yes, magnitude is your values, of course. Okay, great. So, this is actually the result that they achieved on AlexNet. On AlexNet, so we can see that they pruned the yellow. This is bars that could exist of the pruned parameters and the real parameters. So so we can see that they pruned most of the a lot of parameters they could prune and achieve very good results. So from this work has actually showed how to prune most of the parameters in the fully connection layers. Yeah, again, so here they show that accuracy that they only need a few parameters for getting the same accuracy, the same accuracy. And if you're pruning more, so you have some points that pruning there, it's actually you have a very fast degradation. So it's actually like so you can, so here they should stop and not prune again. Okay, so this work was done by, okay, great. So another work that done by on pruning is this work. It's accepted to NIPS 2016. Pruning with rehabilitation, okay, or dynamic network surgery. So again, what we the other work actually we pruned, and then we calculate our loss, and then we pruned again. So this work is actually we can prove we are pruning or dynamically during our training. Okay, so pruned connections have no chance to come back. So if I prune something, I cannot restore this data. Okay, so incurrent pruning may cause severe accuracy loss. So in avoiding the risk of irretrievable network damage, we can improve the learning efficiency by doing this algorithm. So 1 minute, okay. So what we do again, we will look briefly. So dynamic network surgery updates only our weights k and parameters tk that based on some other parameter during the training. So again, so we are pruning. We are choosing, okay, so how the algorithm works, we choose neural network, we train the network until a reasonable solution, we update our parameters tk based on some function that we defined before, and we update our WK matrices based on backpropagation. So the result of actually the backpropagation give us information for which of the weights are used or which not, and which of them we can reduce. And this we are doing iteratively. So we are working, we are dynamically changing our rank of matrices, okay? And by actually by choosing only the parameters that actually are using for the classification or other problems. So its work was extended work for the previous work, and again this work they shown. So we can tune. We can make more. We can prune more rather than Han et al. This is the previous work without dynamic rehabilitation and having better results. So we can actually we are removing by twice the number of the parameters. Okay, so let's continue, guys. Okay, so in the first part, I have talked about how to reduce the computational using pruning algorithms, and I present you a few works that actually a few basics works that have done in this field. Now we will talk about the other way to reduce the computational complexity is by quantized your parameters. So what is quantized? What is quantized? Quantized is actually making your parameters low precision. Okay, so the first work or in computer science, most of the works are done using floating point precisions. So and low precisions is actually the representation that are less than floating point. So when you use and very low precisions is actually it's binary. Okay, so binary is the extreme case of quantization. Is using all binarization. There's only one that you can represent your parameter by 1 bit. Okay. So, and from 32 bits to 1 bit, it's mixed precision or quantized precision. Okay, great. So now we'll talk about a few, a batch of works that done in this field. The last work is mine work, but I will not cover it. You can show it. You can You can see it using my Scholar profile or using the slides. So let's start from full quantization. So using fixed point format. So limited precision arithmetic, where we define the Q initial and the QF, where QI and QF correspond to the integer and the fractional part of the number. Okay, so the number of integer bits is actually some offset IL plus the number of the fractional bits FL, and this way we yields the total number of bits using to represent the number. Okay, so our WL is actually IL plus FL. Okay, and it can be represented like a tuple of IL and FL, where the limits of the precision to floating point to FL bits. Okay, so the range. Our new range, actually, when we're dividing our number, the range is from minus 2 on power IL minus 1 to IL minus 1 minus this fraction. Okay, so this way we actually taking our parameters and divide it to integer representation. Okay, by it depends on the precision that you want to get. So then actually, if you have 8 bits, we divide it. So we have we divide it from to maximum 2 power 8. Okay. Okay. So let's see how the rounding mode works. So we define some x is the largest integer multiplier, okay, of some of our epsilon. This one. So and we do rounding. So when we have x is actually our floating point parameter. So he is usually from infinity to infinity. Yeah. So we are clipping. So if our number is between this one and x plus our epsilon divided by 2, so this will be the x. And when it's x, and when we in this range, we have x plus our epsilon, okay? So actually we divide our numbers to discrete numbers, okay? So we are taking continuous relaxation of numbers and we convert it to discrete parameters, okay? So now we have discrete numbers. Great. So and then stochastic rounding, or actually how we do stochastic optimizations. When we have our x, it will be in this is their stochastic relaxation, and if we have x plus epsilon, this is their stochastic relaxation. Why we need stochastic relaxation of the parameters, guys? Any rumors? Why I can't optimize these parameters? Why I can not optimize discrete parameters? I asking again. Oh, oh, because as we know, stochastic gradient descent or other optimizers working on differentiable parameters because we need to derive our function. Yeah, this is the way how we can find our min max. Great. So if we converted our parameters from a continuous representations like floating point to integer, it means discrete representation, we should to be aware how we can optimize it. Okay, we need to find a way how to find derivation, how to find how to use the stochastic gradient descent to optimize it. So here this work is proposed to use this relaxation. Okay, so what we are doing in the forward step, we divide it for discrete numbers, and when we want to do backprop, we use this relaxation for updating the parameters. Okay, questions? Right. So if x lies outside the range ILFL that we defined before, this is our range. If we are out the range, so we are rounding it to the maximum and the minimum. Okay. So if we above FL, we setting to FL, and if we below IL, we are setting to IL. So we are actually rounding it to the to be fit to our range. Okay, so great. So let's see how Mac operation working during training. So A and B are two vectors with fixed point format, as we defined before. So we compute some z, that it will be actually the summing of AI BI, and the results is actually fixed point number with format, this one. So we convert and round z to be fixed to fixed point format as we worked before, and during test with fixed point format we are and then we actually using backprop on the relaxation, and with the during test we are only convert our floating parameter to this format, and this way we training net to be aware to quantized parameters, and we can use during inference only by applying our integer numbers, and this way we can reduce the actually because the computational complexity, because in hardware using lower precision parameters, we need less energy to compute them. Okay? Okay, so full quantization fixed point format. Okay, so experiments that were done on MNIST is actually the basic data set. They have shown that when they use this algorithm, so they reduced the parameters to 12 bits and achieved same accuracy than on floating point. Again, this is one of the first work. They took MNIST, it's very small scale algorithm data set. So actually, it's like toy example. They and the result was okay. But again, MNIST you can achieve the results with any algorithm. So it's actually it was proof of concept, but then it's not really justified by applying it on large scale architectures and data sets. Okay, so it happens in ICML, top-notch conference, 2015. What happened there? So yeah, okay. So other work that its name is compressing deep convolutional network using vector quantization. Okay, they propose to use codebook and converts our that codebook will consist of the vector quantization. It means that each cell we actually learn the codebook is like we have some we have a book that we can learn how many bits we need for represent each parameter, okay? And then we update this codebook. So we quantize using, okay, first we make quantization using k-means. Okay, k-means is an algorithm that making clustering. So we find the number of clusters as the number of the integer precisions that we want to get. Okay, then we perform to find k-centers. Okay, for weights. Then we minimize our CZ by compression ratio. Okay, the product quantization is actually the partition of W column wise into S sub matrices, and we have some matrices. Then we minimize. We perform k-means for elements of our weights to find k centers. Then here we actually get compression ratio. We maximize the compression ratio, and we quantize the vectors into k centers. Okay, so and recursively we quantize the residuals for t iterations, and this way we actually we optimize the size of our codebook to represent of each vector to getting the best results. Okay, to achieving the best quantization codebooks that we could for getting better for getting better accuracy. So this algorithm, this method calls vector quantization by using codebook. Their results was pretty better, and they actually use they use a larger data set. They use Cipher 10 and Cipher 100 to evaluate their method. And again, they in this way they use 4-bit. They can use 4-bit and achieve actually results that pretty close to floating point operations. Great. So this is the comparison they make comparison with prior work, and they shown that they can achieve better results than others for smaller precisions. Great. So this work is done by Carbo and Joshua Benjo. Again, in NIPS, they presented in NIPS 2015. So this is the first work that they used only binary connections between instead weights. So they used for weights only 1 and -1, okay? So they replace many multiple accumulator operations by simple accumulate. They actually, when you use binary weights, you can replace multiplication operations by summing, okay? And as we know, summing is the factor of the using of the energy to do summing and to do multiplication. Is actually a big difference, because summing is very energy efficient operations rather than using multiplication. Okay, so this work is used. Okay, so they have they have fully full precision copy of their weights. Full precision, it means by they have a floating point operation, floating point representations of the weights, and but during inference, during feed forward, they replace it by binary connections. Okay, great. So as I said, fixed point adders are much less expensive, both area and energy. And how they did it? So the deterministic binarization. So when the W is higher than 0, it's 1, and otherwise it's -1. And the stochastic binarization that they did is actually when it was +1 with probability P and -1 with probability 1 minus P. It's like Bernoulli probability, yeah? So then they actually learned the clipping. They learned the sigma x. It's actually, they learned when they need to do the threshold. So which this was did by start. So they initialize it in this way, and then they learn the clipping, or actually when we need to cut. Okay, and this is it. Is it understand? Is it clear? Guys, you please ask if you have questions. No? Again. So first, we have our weights, okay? We have our weights. 1 minute. So we have weights. So this is range of our weights, okay? From minus P till plus P. Okay, this is our original weights distribution. First, what I'm doing, I'm taking the new distribution and I'm cutting by 0, and these numbers are -1, and these numbers are 1. Okay, then I propagate it. Once and what I'm doing during backpropagation, I'm learning the sigma, and sigma x is actually clipping, where I should do my threshold, where to cut. Okay, so here I've defined the cutting on 0. Okay, so now I want to find actually where should my sigma cut, here or here or here, or okay, this is where the number that below it will be 0, -1, and the after will be 1. Okay, I am learning parameter of clipping. I'm learning the parameter of where to cut the number. Again, here, yeah, sigma. So I'm do clipping, okay? So I'm do clipping on of my of so I'm clipping the number by like by 0 and 1. Okay, so it's convert to -1 and 1. Okay, so it doesn't matter. You are only finding two numbers. Okay, so you in binary network you have only to represent 2 bits. Okay, so if you it's actually after value, but it's okay. That doesn't matter. So you are need to learn 2 numbers. Okay, you need to decide in which number to represent for each weight. Yes, of course, but I want to learn the I want to. No, not by changing by changing. Again, I have distribution. My weights was fully were trained before. Okay, so I have some distribution. My weights have some distribution. Of course, guys. All these algorithms are working after you pre-trained. This is not from scratch. Okay. This was the problem. Sorry. So you should start from something works. You cannot. So once you have some distribution, now understand. So you ask where the distribution. Yeah. So you have your distribution. It's already been done. It's learned. Now we are initialize our parameter. We initialize from taking the health. Okay. So the first half is one number. The second half is another number, and then we are learning where we should cut. If it's health or maybe in some other part. Okay. Yeah.
What, are these two different kinds of the binarization? I mean, the clipping. Do we learn it differently for stochastic or deterministic?
No, for deterministic, it's only it's actually it's what we do only during test. Okay. And stochastic is what we do during the training. So how to train it? Okay. So this is done during training. This is only during test. Okay. So and the clipping is using for changing the probability of stochastic. Okay. So again, we this work proposed to way to replace the weights to binary weights. Okay. This is the this is this work. Okay, so and this is the explanation. So for given DNN input, we compute the unit activation layer by layer leading top layers, which is output of the DNNs. This step is referred to forward propagation, and then the given DNN target computed the training objective gradient, each layer activation starting from the top layer and going down layer by layer until the first hidden layer. Okay, this step is referred to backward propagation. Okay, or backward phase, and then we compute our gradients, each layer's parameters, and then update the parameters using their compute gradients to previous layers. And of course, again, as I said before, we update the gradients that we restore them in full precision. So we have one copy of full precision weights. We are finding the gradients of each weight, and then we update the full precision copy of weights. We're doing it once at epoch. Okay, so we are doing this. We are calculating, updating the original weights, and then we are binarize at the next step. Questions? But of course, it's less expensive because you are only once at epoch updating the full precision weights. Okay, so most of the computational are done on using binary parameters, and once at epoch you are updating your full precision. Guys, questions? Great. So yeah, so actually we talked about it. So binary only binarize the weights during the forward and the backward propagation, and then but not during the parameter updates. Parameter updates doing on full precision. Great. Yeah, so again, we talked about it before. So this is our algorithm. So we are taking, again, here we again, how we do it. I will not, we talked about it before. So great. So this, okay, so this work is actually, it's binary connect. So they shown that they achieve better results rather than using previous works, and with less degradation on accuracy by less computational complexity. Okay, so the prime motivation is the neural networks with both binary weights. So the other, okay, so now, okay, so now I will produce, this is the work that they actually, it's the continuous work that here they do not only binary weights, but also binary activations. So actually, all the pipeline in the forward, in the forward, in the feed forward is doing on summing numbers. So you're only summing numbers. So it's tremendously improve your actually the power consumptions of your neural networks. So and you're doing also binary weights and activations, and then the gradients. Then you compute gradients, and again the updating of the gradients done on full precision. Great. So a few highlights of this work. We're propagating gradients through discretization. Okay, we are actually propagates our gradients through discretization. So straight through. Okay, so now we are not only we are this work is proposed way how to propagate during discrete numbers. So how they do? They defined Q is sine, is like a sine, and then they estimate their function, their gradients quantized of the gradients, okay, and then they do rounding. So actually, it's like a stochastic rounding approximation. So it was first, so the common name is straight through estimator, or STE, it's the abbreviations. The algorithm itself is proposed by Benjo a few years before this algorithm. So he proposed how to update gradient descent on discrete numbers, and these guys applied their quantization method to how to propagate through the quantized discrete parameter. Okay, so they replace the multiplication with bit shift, okay, and replace both batch normalization with shift-based batch normalization, and they replaced the Adam optimizer with shift-based optimizer for doing discrete optimization, okay? Because they're rather than different, actually different derivate, they only use shifting because they're using on it's only it's quantized numbers. Okay, so you can, instead of doing the derivation, you can use shift for derivate. Great. So this work propose both quantization of weights and activations, and how to propagate through them. And again, this is their results, and they outperform they did it on M instance on Cipher 10, and they upbeat the previous works. Okay, so quantize, it's actually how GPU kernels execution time. So as we can see that the baseline is the baseline matrix multiplication, and when when we use Kublas, it's actually the inherit function. We can reduce dramatically the time that we need for computational on binary on quantized on quantized parameters. Okay, so it was the introduction for pruning and quantization. In our Vista lab, we are doing a lot of works in this style. So actually, I'm in charge of this subject. So the people who wants to work with me will shall tell you the project that actually this week I'm going to publish you projects for this semester. So there are a lot of works on optimization and on optimization of neural networks, and this is what I'm doing, and other actually, and a lot of other stuff. So you are invited to choose these works and work with me on them. Thank you.